there is addiction, because we want to know not just what's happening now or what happened in the past. We'd like to be able to know what's going to happen in the future, because that lets us collectively make more intelligent decisions, whether it's, do I bring an umbrella? Do I wear a heavy coat? Or even things like, where do I build my house? Where do I retire? If I'm a business, where do I want to invest my capital? What business do I want to be in? If I'm a government, how do I want to provide the infrastructure to serve our citizens into the future? You want to have predictive capability for that, because you can't just extrapolate into the future. We've seen that the Earth is just too darn variable to be able to do that. So that's the paradigm: variability, forcing, response, consequence, and prediction. So in NASA Earth Science, then we try to work in all of these areas. There's a number of things that we can do. Scientific knowledge, from basic discovery, process knowledge, trend detection, which is important because people want to know what's changing, and attribution, because they want to know if it's changing, why it's changing. And we want that forecasting capability because people want to know about the future. There's some applications to national and global needs, because studying the Earth, people do make decisions. So that means there's environmental policy, resource management, forecasting and assessment, and decision-making that people and institutions do. So I'm going to talk a little bit about all of those. As an R&D agency, NASA contributes to technical capability for space and airborne systems. We provide environmental data for public use. One of the things that we do is make our data routinely and readily available, essentially to anyone in the world. We help create a trained workforce for science and technology. There's a lot of students in this audience, and you are part of that trained workforce for tomorrow. And finally, we have a better informed and inspired public. NASA in general does a great job at inspiring students. Many of us in this business are in it because we were inspired by NASA's accomplishments in the past. And especially for the things that we're doing, I think learning about our home planet can help train and inspire students for the future. So it's not well understood, but from a US governmental point of view, NASA is actually the largest contributor to the US Global Change Research Program. If you look at the reports that the government puts out every year, and you can see Our Changing Planet on the right-hand side, it's an annual report to Congress. Look at the budget tables there. NASA provides more than half of the US government's investment. It's identified as part of the US investigation in climate change research. There's a lot of documentation that people put out. There's other administration initiatives, but we're certainly not doing this by ourselves, and we do it in a way that's integrated with other federal agencies. The last time the US government actually did an integrated plan for its climate research was done under the previous administration in 2003. Back then it was CCSP, the Climate Change Science Program, because the previous administration wanted to change the name from the Global Change Research Program that harkened back to previous administrations. So they're in the new administration, and we're back to the Global Change Research Program. These things do happen. But there were 5 main goals in the strategic plan from 2003, which is actually the last strategic plan that we have for the program. The next one is being written as we speak, and my 10 a.m. meeting Friday is to help write the next strategic plan. But there are 5 goals, and the ones in red are the ones that NASA is primarily focused on, because at NASA, we don't regulate, we don't make policy, we don't really manage things other than our own centers. So we want to advance the science, we want to do the quantification of forcings and improve projections, but a lot of the other things that the government has decided are important are not things that are historically NASA's strength. So we don't do that much at it. We try to expand our national capability so that people who want to do those things in blue can do them on a sound, rigorous basis that's well informed by observations. In 2009, the administration put out a report on global climate change impacts in the United States, and it was focused on the US. It was an interesting document, and full disclosure, I'm one of the members of the author team for that. So if I say it's a great report, which I think it is, in some sense, understand that I'm conflicted. But it made a number of comments about climate change, and it's a report that was started under the previous administration, finished under this, and it made some strong statements about it. I'm not going to go into a lot of details on that, because in the talk that I'm giving, I really want to focus more on the rest of the world. This report had a strong domestic focus, because that's really what we needed to do. But there are a number of things just in terms of observations, and one of the points that report made very strongly was people looking at the past 50 or so years of data show that there's some long-term changes that have taken place in the United States, whether it's increases in very heavy precipitation, winter temperature trends, observed droughts, and sea level changes. So it's not just a modeling exercise, that there are things that people have seen in the US, but a lot of this stuff that was in there didn't come from satellite data. But when one gets to the rest of the world, the satellite data that NASA provides are more important. So that's what I'm going to be doing. I'm going to mainly be talking about the rest of the world and showing a number of examples of what happens when we look at the Earth from space and what we're seeing. As part of doing that, I want to be very clear about how we do this, because we tend to take it all for granted. But it's a marvelous sort of scientific and engineering accomplishment that we work on. We've got 13 major operating satellite missions. We've got a bunch of things that I'm not really counting because that's like putting one sensor on somebody else's satellite. 13 major missions. If you count really quickly, you'll see there's 15 on there, but 2 of them have X's in there because they stopped working. Space is actually a fairly hostile environment, and things do not live forever. We actually do pretty well. You can see the international aspect. The flags reflect our partners in doing this, and this is a mix of small satellites, big satellites. The oldest one, TRIM, Tropical Rainfall Measuring Mission, a partnership with Japan, 13 years old. The newest one, Ocean Surface Topography Mission for measuring sea surface height, a partnership with France, launched in 2008. And the ones with X's, QuickScat up at the top. It's actually still working. It's just that it needs a spinning antenna that doesn't spin. So it just measures straight down, but it's actually calibrating a satellite from India right now. That one died 10 years into a 2-year mission. Not bad. The engineering aspect of this is significant. So we do want to recognize that the first thing you have to do is launch. And this is from the last launch, successful launch that we have for one of our satellites, the Ocean Surface Topography Mission.
Liftoff of the Delta II with Jason 2 for the Ocean Surface Topography Mission, measuring sea level from space.
It's a launch, but it's, you don't take these things for granted. If you really catch things very carefully, you'll notice that I said the last successful launch that we had, because the last launch that we had, the Orbiting Carbon Observatory in 2009, was not successful. So we're now working to try to rebuild and relaunch. If you actually look at what it is that we do, typically, most of our satellites are in what we call polar orbit. They're 700 to 900 kilometers, or 400 to 500 miles or so above the Earth. It takes about 90 minutes to go around the Earth. The Earth is spinning as you do it, so you're not actually staring at the Earth. You kind of have to piece it together, because when the satellite gets back to where it was before, the Earth has moved. So the time zone problem. If your sensors can swing back and forth, you can almost cover the globe in a day, or twice a day if you can measure in day and night. But the satellite's moving 7 kilometers a second. The Earth is turning, and when the satellite's moving, every 90 minutes, it goes from the darkest, coldest night of space, almost instantaneously, to the full force of the sun on you, makes that transition in seconds, and then 45 minutes later, it goes back around. So the satellites take a beating, and they do this 16 times a day, day after day after day, year after year after year, to the point that some of these satellites, not the ones that we've got now, if they were teenagers or whatever, they'd be old enough to drink and old enough to vote. If they could, they wouldn't be teenagers if they could drink. But it's a fundamental engineering achievement that we have. The other thing is that when you actually look at what the satellites are doing, they're using solar power. The solar panels are turning. Sometimes you have to turn the satellite around to get the sun. Again, it's a phenomenal engineering achievement that if you're a theoretical scientist like me, you tend to take for granted. We should not. And it's one of the great things about this work that we do. It represents such an intimate partnership of science and engineering to be able to accomplish our aims. Now, the satellites are not up there just flying all by themselves. A lot of times what we do is we put them together in what we call a constellation, where they're flying in very close proximity to each other. So the main one is called the A train, because sort of the linchpins start with A, Aqua and Aurora. But then we've got a couple of others in there. CloudSat and Calypso are in there. they're flying 17.5 seconds apart. So there's a very active control. Again, this is a significant engineering accomplishment. It's also, in some sense, a political feat, because what you have to get people to do, including people from outside the US, to give up some control of their own satellite, because if you're flying that close to each other, you can't just do whatever the heck you want to, especially if you have to move it to try to avoid space junk. Well, you got to make sure that you don't move your satellite to block somebody else's. So you'll see the one that's just a little bit below, it's called Parasol. It was actually a French satellite, but when they were losing the ability to control it, we moved it out of the constellation so it wouldn't endanger the others. And the constellations can come and go. It's a great way to get near simultaneity without having everything on one platform. You wouldn't want everything on one platform. It would be too big, too complicated, too much launch risk, and probably just too expensive to do all at once. So you can build the constellation over time. 2 weeks from today, the one that you can see called Glory is going to launch. I'll say a little bit about that later. And if you look all the way at the left end, you'll see, or I guess the right end, you'll see GCOM W1. That's a Japanese satellite that hasn't launched yet. And the OCO-2 is when we refly the Orbiting Carbon Observatory in 2013. That'll join the constellation. So this way, again, it's the benefits of simultaneity without all the risks and complexities and hassles of doing it. But simultaneity is important because it's almost as good as having everything on the same spacecraft. And that kind of thing really is important because, look at clouds. Clouds can move very quickly, If you look at a cloud and, you look 5 minutes later, it could look very different. So simultaneity is important. Now, one of the things about satellites that's really neat is you've got the same access to remote and hostile areas. I talked about 16 times a day over each pole. Without satellites, there's no way you're going to do that. Folks here do a lot of work in Greenland. They may do some on aircraft, but where you can do it on satellites. If you want to know what's going on over the open ocean, over deserts, over tropical forests, over volcanoes, you just can't send enough people out there. So we say, for some of the polar stuff, for the things I'll show you about Greenland, you could not send enough graduate students and dog sleds out to make those measurements. And besides, if you did, it would be cruel to the dogs. But there's also the sense that even in developing countries, you don't have the measurement infrastructure. And in some sense, satellite doesn't care. It just flies above you. And as long as you can be sure that your satellite measurements are accurate for the particular set of conditions that you're flying in, to first order, the measurement is as good everywhere. And with one sensor, we can cover pretty much the whole world and make that data available to everyone in the world, including the developed countries that don't have the infrastructure to get the data. It's hard enough to give it to them sometimes. But we try and work it with that. So what do we see? Well, one is that you can just sort of get snapshots. Look at sea surface temperature. The red colors are the warm colors, so that's the Gulf Stream. Some sense, that's just pretty. I think it's cool that our planet has such structure, You say, why is it there? You can think about the motions, I'd probably frame this picture and put it up on my living room wall if my wife would let me. I just think it's absolutely gorgeous. But, that's a snapshot in time. But then you try and watch the Earth system evolve. So you can look at hurricanes. This is for the 2005, which is a very active hurricane season. The blue are sea surface temperature measurements from a Japanese instrument on one of our satellites. And as the hurricanes come in, you can see the tracks, see what a busy year it was. So blue is cool, yellow is warm, orange and red are warmer. And you can see as you get through June, some of those yellows are turning into oranges and turning into red. Not many hurricanes early in the year. You can see where the clouds are. Then you get to see hurricanes go alphabetically. So now you're up to Cindy. Then you get Dennis. 2005 is getting to be a while ago, so we forget how many there were and how many times they made landfall in the U.S. You can see Emily hits the Yucatan Peninsula, hit Texas, Mexico right around Brownsville. Some of them just kind of rattle around off the ocean. Notice now you're getting into the August. You're seeing a lot more oranges and reds than you did before. So, we're getting the seasonal view, and you can begin through satellites to tie the fundamental underlying conditions of the planet to what the planet is doing. You can see the hurricane tracks. See, you're up to Irene, so, you can think, well, when do we get to Kaye, Katrina? And see how much warmer the Gulf is at that point. That's one reason it had that power to go up, track through the U.S.